Okay, morning everyone. So I hope you're relieved that the midterm is over now. They have been marked, but I haven't actually looked at the marks yet. So I imagine you'll get them back tomorrow in tomorrow's recitations. So for today, we could go through a few of the midterm questions if you are interested in doing that, or we could just push on with the next chapter. What would everyone prefer?
We could go through the quiz during the recitation.
Yeah, I don't know what he'll go through exactly in the recitation, but I mean, we will obviously coordinate so that, we do it on demand. So, whatever we do here probably wouldn't be repeated in the recitation. So, basically, this is sort of gives you extra opportunity to go through more of the questions because I don't think you can go through maybe both all the quiz and all the midterms in the recitation. So do you want to go through any particular problem from the midterm? No? Not really? Okay, if nobody wants to do that, then we can just push on with the lectures, yes? Or do you want to revise anything? Okay, no real demand. So then, in that case, I guess I will just go on to the next chapter. So this is chapter 8, potential energy and conservation of energy. What's that? Okay, so this chapter is basically talking about other forms of energy. So in the last chapter, we encountered kinetic energy and work, and one of the main results of the last chapter was the kinetic energy work theorem. So basically, we can sort of picture that as, if you remember my bank account analogy, we can picture sort of kinetic energy as being one bank account, which keeps track of how much, in this case, energy you have. And work was basically the amount of energy, really, that's actually flowing into that bank account. So work is always associated with the transfer of energy between two things or two parties. This is how it was described before, but actually you can also have more than one type of energy. So this is the idea of potential energy. So you might think of this as saying that, maybe the bank account analogy would be that, one person might have, dollars or RMB or maybe euro, So you might have different forms of currency, and what we're going to basically do is to kind of look at potential energy, which is basically kind of like, you can think of it as another type of bank account in which to store energy. Okay, so let's first define potential energy. Probably most of you, again, have encountered this already, or it's kind of a pretty famous concept. So potential energy is energy associated with the configuration of a system of objects exerting forces on each other. So two classic examples are elastic potential energy and gravitational potential energy. So in the case of elastic potential energy, so you've got this girl here that's pulling a bow. So what's really happening is that she's putting energy into the configuration of the atoms there. So the string of a bow is made up of some kind of elastic material, and it tends to want to sort of jump back into its original configuration, so that you might have, for example, I think rubber is made of like sort of these long polymers, and they're all sort of intertwined kind of together, and then when you stretch it, it tends to want to sort of come back to its original configuration, and the energy is actually stored, essentially sort of chemically, because if you look down to the molecular level, all the atoms are, they have now some forces between them, and they're trying to pull themselves back into the original configuration, and this is basically where all that energy is being stored. So it's basically this string is pulled into some weird configuration which this polymer doesn't really want to be in, and it's trying to fall back into the original configuration, but something is preventing it from doing so, right? So elastic potential energy, gravitational potential energy is, so if you high up, then you can, if you jump off a cliff or something, then basically all that potential energy can be eventually converted to kinetic energy. And so in each of these cases, you might sort of think of this potential energy as being something where you can easily re-extract the energy back, right? So it's almost like a battery, right? So batteries are good because you can kind of store energy in them, but easily get them out again, right? It would be kind of pointless, or it wouldn't be a very good type of potential energy if you couldn't really get the energy back, right? So if I gave this, some amount of energy to this table and heated up the whole table, it's hard to get that back, right? Like I can't re-extract that energy back very easily because it's sort of just kind of gone, and it just dissipates kind of into the room. But for things like elastic potential energy, gravitational potential energy, or elastic potential energy, all you have to do is just release it, and then you got all that kinetic energy back, right? So it's kind of a good storage medium for the energy. Same with the gravitational potential energy. Just have to jump off, then jump off the cliff, and you got all that kinetic energy available back to you. So it's not that sort of everything is kind of potential energy. It's usually only for certain things which are relatively convenient to get the energy back. Right? Okay, so how do we define it? So we're going to start with a slightly weird sort of looking definition, which will probably appear a bit confusing, but the change in the potential energy is related to the work, which is the amount of work that you that is actually done by the particular force, according to this relation, which is that. Where's my mouse? Mouse is gone. Where is it? Somewhere. Here we go. Yeah. So it's the negative of the work. So the change in potential is the negative of the work that is done by the force, right? So, when you look at that, it looks a little bit confusing. You sort of don't kind of understand why it should be the negative of the work. But if you look at an example, it sort of makes a little bit more sense. And keep in mind that the kinetic energy work theorem, what we said there was that the change in the kinetic energy is equal to just the work, right? not the negative, the work, but the positive sign work, right? So, so what's with the negative sign here? So let's look at this particular example. So we're going to look at the work done by gravity when we are, say, throwing this apple in the air. So we throw it up and then say catch it again. So it's going to go up by some height h, and then it's going to fall back down. So let's look at the two paths of this. So we're looking, and always we've got to be careful of like, okay, so what force are we talking about here? And so the force is not my hand that's throwing it up. It's actually the work done by gravity in this case. Okay, so on the way up, it's displacing up, right? So the movement is up, but the force of gravity is down. Yeah. So negative work is done by gravity, because the force and the displacement is in the opposite direction. And then, so according to the kinetic energy work theorem, the kinetic energy change is negative mgh. Right? And so that makes sense because when you initially throw the apple up, so we're just giving it some initial velocity, initially it has some high velocity here, right? And at the top here, the velocity slows down, and so the kinetic energy is actually lowered, right? So it goes from some kinetic energy here to some other thing. Now, if you actually think of where that energy has kind of gone, and basically the answer to that is that it's basically gone to the potential energy instead. So the kinetic energy is decreases, but the potential energy actually increases instead. So this is basically why this has got a negative sign. Work is always associated with the transfer of energy, and so there's always a kind of a gaining party and then a losing party, right? And basically what the kinetic energy work theorem was saying is that, I think I'll do this in a slide in a minute, but basically the kinetic energy work is the amount of energy that's transferred, and then so the kinetic energy, this is, say, the initial configuration, then some work happens, and then kinetic energy is actually changes according to delta K is equal to the work. But we basically didn't say where it was coming from or going from, so that there's always a we were only talking about this, but we didn't really ever talk about, so, what is, sort of, where is that work actually kind of coming from? So basically, this sort of fills in that hole, if you like. So the potential energy instead increases when it goes up. And so because one gains and one loses, has this negative sign. So on the downward journey, I think now it's probably pretty clear. In this case, gravity is down, displacement is down, so the work is positive. The kinetic energy increases because falling objects get faster, of course. And if you ask where did that energy come from, well, it came from the potential energy, and so the kinetic energy has gained at the expense of the potential energy. Oh, it's a tomato. Okay. Right. Okay, so hopefully that's clear. And we could do a similar game with a spring or some elastic potential energy. So, for example, let's say what we're going to do here is we're going to compress this spring. Yeah, I'm doing here, compression. Yeah, so here's the equilibrium position, 0. So we're starting here, and then we're ending somewhere over here. So we're going to compress the spring. This is the equilibrium position, so that's how I know that this is, it's going to be compression. And so the force by the spring, the spring is always going to kind of try to oppose this compression, right? So the spring is trying to, you're compressing it, so it's trying to push outwards. So the force is to the left, the displacement is to the right. So because they're in opposite directions, we know that the work is going to be negative, yeah? And I mean, you could do a more exact calculation according to that formula that we had in the previous chapter, but the main thing here is it's negative. Work kinetic energy theorem says that, the kinetic energy is going to be, change in kinetic energy is going to be negative because, basically the kinetic energy, say you started with some velocity here and then you're compressing the spring, obviously it'll slow down, right? So you're pushing against a spring, it'll slow down. So the kinetic energy will go down, it'll become slower. And basically what we're saying here is that it happens at the expense of the potential energy. So potential energy goes up. In this case, it's the elastic potential energy of the spring. When we're looking at the reverse, so when it's starting here and then going outwards, this time we're going in the same direction as the force. Spring is now bouncing out, moving this way. Force and the displacement are in the same direction. The work is positive. Kinetic energy is also positive. And obviously it's because you're starting here, you release it goes boing, and then the thing goes flying, so the kinetic energy increases. But that happens at the expense of potential energy. Okay? So it always has a negative relationship. Yes, so I guess I already basically said this. So I already said that, we know from work kinetic energy theorem it's that, but here we're saying this. So here's the kind of money analogy. So kinetic energy work theorem, what we were saying is that the amount of money flowing in here is equal to the change here. So if this is $2, then obviously this goes up by $2 because $2 is flowing in. So obviously the bank account goes up by 2. We never really talked about what was happening over on this side. So here, obviously, if this guy is paying this guy $2, then his bank account goes down by $2. So it's just that. So, in a money context, it's absolutely obvious, right? So obviously if I pay you, then my bank account goes down, your bank account goes up, right? So that's basically all we're saying. Okay. So, right, yeah. So now we're going to talk about another concept, which is called a conservative force. So in the examples that we've looked at before, all of these were so-called conservative forces, and the kind of the signature of this is that when we started, say at this point in the spring example, what we did was to compress the spring, and then we came back and then we released it, right? So the after the two-step process, the block is at the same position, right? And what we were saying here is that the work done by the spring is going to be negative here, but it's going to be positive here. But if you look at the actual formulas, so for example here, this is minus half k x2 squared minus x1. This is minus half k x1 squared minus x2. So this is exactly the negative of that one. Yeah. This was also true over here. This first leg was the same as the second leg, like the magnitude of it, but just with the opposite sign. So they were numerically exactly the same. So these are examples of conservative forces, and this is actually not always going to be true. This is, again, a kind of an idealization. It's a little bit like, well, actually, so friction is an example of a sort of a non-conservative force. So in these two examples, they're sort of kind of ideal cases. And in kind of real life, often the forces are not sort of perfectly, the situation may not eventually have a conservative nature because of imperfections like sort of friction. So this is more or less what we're talking about here. So and the kind of immediate test that you can do to check whether a force is conservative or not is to basically just do exactly what I was saying. So start and end in the same configuration. So that means usually position, right? So notice here the velocity could be actually moving in opposite directions, but in the case of sort of potential energy, the velocity doesn't really usually matter. We're kind of more or less talking about only the potential energy here, and so we've got the same configuration, start to end, and we're going to test whether the work done in the forward leg is the same as the backward leg. This is the kind of the test. So more abstractly, this is kind of what we this is our sort of definition of a conservative force. So we do a kind of a loop test. So this is kind of an abstract space. So it's this figure here, you might sort of think, well, what is this figure even plotting? But what this figure is trying to get across is, so perhaps this could be anything, but an easy example here would be again position. So for example, let's say this is the XY coordinates of something, I don't know, whatever it is, in some space, right? And so the initial point we're calling A, the final point we're calling B, and of course they have some coordinates, right? And so you can get from point A to point B using multiple paths in this kind of two-dimensional situation, right? So you can go from A to B along this path, or you could go from A to B also along this path, right? So there are multiple ways of getting from point A to point B, and this would be certainly true in a spatial situation, but this is trying to say something a little bit more even general. So maybe this is not even position necessarily. Maybe these are just some some other configuration of the system. So, I mean, this goes a little bit beyond what the textbook is saying, but maybe another example might be something like, say you had a bunch of, two-level systems. Okay, so suppose, let's use a coin, I suppose, right? So the coin could be either heads or tails. And say you got a bunch of these coins, right? Heads, tails, right? So all the different configurations of the system could be like head, tail, all the way down to tail, right? And we could potentially sort of go between two configurations. Say you start in head, and then you end in tail, right? Now you could do that in more than one way, because you could say, okay, I'm going to flip this one first, and then this one, and then this one, right? So that would be sort of one path, right? Or I could flip that one first, and then that one. That would be kind of a different way of going from head to tail, right? Those would be two different ways of basically starting in some configuration and then ending in another configuration. Or I could do something even more complicated. I could flip that, I could flip that again, flip that one again, and then end up in tails, right? So because you could potentially flip the coin more than once, right? There's nothing to say that you can't flip it just once. So this picture is trying to get across this idea. It can be space, like I drew here, but it's more of a kind of an abstract idea of, well, okay, I have one configuration, I have another configuration, and there's multiple paths that I could take to get from point A to point B. And so whatever your system happens to be, the test for whether it's a conservative force is that if you go in a loop, so in this case, I was saying go from A to B in different paths, but so you could go from A to B and then back from B to A, and that would be like a loop. Yeah? So basically, you start and end at the same position or same configuration, whatever it is that you're talking about. And if the net work done, so basically just the sum of the two, so there's some work associated with going here, and there's another work going from there to there. If you add those two together, if they're zero, then it's a conservative force. That's kind of the test. And this is basically a yes or no answer. You go around, and if it's yes, then it's conservative. If it's no, it's non-conservative. Yeah?
If A is head, and B is tail,
yes.
A conservative force will means that I need to also go from tail to head.
Yes, right? That's right. Yeah, that's exactly right. Yes. So to do the loop test, you'd go head to head, tail to tail, and then back to head, and then you add up all the different, the work done in the forward path and then the reverse path. So maybe there's some energy associated with flipping a coin, right? So you'd add that energy, and then when you end up with tail, you look at that's your work for the forward path, and then you reverse the whole thing, and then see if it's the same thing. Okay, that's good. Using this definition, actually, we can actually deduce a kind of an interesting property. So, this is kind of abstract and rather general, but you can already deduce something from it. So let's say we have a conservative force, right? We have some force, and it satisfies this loop test, okay? And it's general, right? So this is just, it's not that, okay, here's just two paths and zero, it's conservative. Actually, you have to do it for kind of every possible path, right? It sort of should be tested for every possible combination. This is just one example. But suppose you do have a conservative force. So that basically means in this loop here that WAB1, what that means is you start at A, go to B along path 1. It's basically what that thing means. This means you start at B, go to A along path 2, and that. And so what we know is that the sum of those is 0. And this implies that the work done by conservative force on a particle between moving 2 points, it doesn't depend on the path taken by the particle. So basically what that is implying is that so WAB1, so the work done here, is equal to WAB. So notice that this is AB, not BA, right? So you go along path 2 from A to B. And so this has to be the same. And I mean, not only that, I guess, eventually if you know it's a conservative force, then you could, do some weird path like this. And basically all those paths would have the same work. And it wouldn't matter which path you chose, the energy would be the same. And so just to, this seems a little bit abstract, so just to give you a little bit of a better idea of this, let's say you're hiking in the mountains, right? So you're hiking in the mountains, okay, snow. And say you're starting here, and then you want to go to here. Now there's different paths. You go along the sort of the mountain ridge there, or you can go here, go up, straight up, yeah, or any other path. Now, okay, in real life, obviously there's going to be some paths that are easier than others, right? But let's talk in a kind of an idealized sense of, there's no friction and that kind of situation. Now, basically what this thing is saying is that it doesn't really matter which path you take. All these, going from the start to end, all take the same energy. So it doesn't really matter because basically the only thing that matters is, in this example, the gravitational potential energy and the work that you need to do to go from A to B is always mgh. It doesn't matter what path. So that's, it's not really a real life example because it doesn't, work for us, Firstly, you would have to be like a ball or something, right? So, not something like a human that walks, because, for example, here, like the reason why, you're actually going higher than B here, right? But basically the point here is that, you'd roll down here, you get that potential energy back, and so you never really lose the amount of energy that you are that you're kind of expending to go up this mountain here. So it's not a real life example as such, but at least it's a little bit less abstract than this one, right? So that's basically the point that this is trying to make, that it doesn't matter which path, if it's a conservative force, which, okay, gravitational potential energy actually is a conservative force, it just doesn't quite work in real life because we bipedal and whatever. but also the mountain is rough, right? But that's basically the point. Okay, so what we're saying here, well, mathematically speaking, is that from this statement we can prove, we should be able to prove this. How do you think you'd do that? So this requires one little kind of trick, I guess, in order to start from basically this statement or this general property of conservative forces and basically end up with this equation. I mean, notice here that you don't even have AB2 in this first equation here, right? So that's already a bit of a hint for you. But so how about I give you a minute to try and figure out how to prove that? Oh, you got it. Integrate it. Actually, for this one, we don't even need to do anything that fancy. The only ingredients that we need is just the loop test statement and kind of applying it in some way. Yeah. Yep.
WBA equals negative WAB.
Right. Yes. Exactly. Yes. So. Yeah, so that's basically the trick that you need to work this out. So let me just redraw it because that's got a bit messy. So our original statement was that, so this is point A, point B. So we're told that this is a conservative force, right? So what that means is that WAB, so going from A to B along path 1 and then back to path 2, sorry, BA2 is equal to 0. But actually we can write two more equations. Not only this one. So what we can equally say is that WAB along path 1, and we can just come back along path 1, right? We never said we'd have to go along path 2 on the return journey. In fact, I'm saying that if it's a conservative force, it's true for any paths, right? I could pick another path. So you can go along one and then come back along one. So how would we write that in terms of this notation here? This is like the start end path, right? So the second leg, what would I write?
Negative WAB1.
Right, yes, but I think you've put it on the other side already, yes, but for now I just want to keep to that format, yeah. Of course, if you put this on that side, then it would be negative, like you said. And then for path 2, I could go from A to B along path 2, and then come back along path 2, right? So actually, we've got sort of three equations, and this is the thing that we're trying to prove here. So we need a relation to sort of turn WBA into WAB, right, according to this. So what we can do is we can use the first and the third equations. So let's use that. So from the first equation, we can say that WAB1 is equal to minus WBA2. Okay. And then from the third equation, we can say that WAB2 is equal to minus WBA2. Okay? And then we can simply just equate these two because the right-hand sides are the same. Is equal. So WAB1 is equal to WAB2. So that's basically the that's the proof of this. So yeah, so you don't actually need to do anything explicit in terms of calculating the expression for the work. You just have to kind of use this in a bit of a clever way. Yeah. So yeah, so this basically says that it doesn't matter what path, if it's a conservative force, it doesn't matter what path, or my mountain analogy, any path is fine. So that's basically what that means. Okay, so let's give you, just to give you a little bit more of a feel for what is a conservative force, what is a non-conservative force. So let me give you examples. So I've already said that gravitational potential energy, elastic potential energy are kind of non-conservative forces. It's actually kind of pretty hard to think of a purely non-conservative force, but you can consider perhaps at least this situation to be a non-conservative situation. So for example, if you threw up the apple, tomato, in water, this is kind of a pretty clear example that you're not going to, the energy work done by the gravitational force going here is just simply not going to be the same as it's actually not really the gravitational force. Sorry, I just copied this figure, so maybe this is not completely accurate, but it's more like the work done on the tomato, like the total work done, so the combination of the gravitational force and the frictional force. So that combination, if you look at the work done for that situation, for that combination, then it is not a conservative force because basically the frictional force will actually make this different on the forward and the backward legs of the journey. Similarly with this, so the frictional force, so this is supposed to be some kind of rough surface. So again, the amount the energy that you're putting into the system will eventually be dissipated, and then you will not get the amount of energy that you just kind of stored in the spring. Some of it will be lost back into the environment. It'll heat up the surroundings, and some of that energy will be lost. So these are kind of non-conservative forces. Okay, so let's continue with our money analogy. So we can think of it kind of like bank fees. Everybody loves bank fees. So when you transfer some money, used to be the case that you actually needed to, well, I guess it's still true, but yeah. So often there's ways to get around it these days, but I think even in China, depending on the amount of money that you are transferring, they sometimes charge you bank fees. So when you are trying to give somebody $2, suppose the bank takes 50 cents every time. Yeah. So when you do say what we're going to do is something like the loop test, right? So what we're going to do is we're going to try and get back to the original configuration. So for example, maybe what I should have done here. I think what I should have done here is call this guy potential energy and this guy kinetic energy. Okay, but all right. So let's work with that. So suppose this is kinetic energy and this is potential energy, right? So what we're going to try and do is to get back to the original kind of configuration. So say this is potential energy, and so it starts with $4, okay? And Mr. Kinetic Energy is going to give the potential energy $2, but then 50 cents is lost in bank fees. So the potential energy is now going to go only up to $5.50, right? And then oh no, sorry. I had it right the first time. So what we're trying to do here is to get the potential energy back to $5. Okay, so sorry, we'll keep it as the same. So transferring $2, losing 50 cents in bank fees. So when $2 is transferred, this kinetic energy goes up to $5.50. And then if we do the loop test in order to get the potential energy back to $2 to $5, we need to actually transfer $2.50 to make up for the bank charges. And so basically, in order to go back to $5 here, the forward work and then the backward work is actually not the same, because basically, in order for the potential energy to get back to $5, we had to kind of make up for the fact that bank charges are being taken away, right? Yeah, so without bank charges, basically you transfer $2 and then this person transfers $2 back, and then basically what happens is that $5 goes down to $3, but then goes back to $5, right? So that's basically the loop test that we're trying to do. But if we're losing to bank charges, then in order for us to get back to $5, on the return leg, we have to actually transfer $2.50 here, so that just to make up for the bank charges that are lost, right? So basically, the forward work is like $2 in this case. Backward work is $2.50, and then so the forward work and the backward work are not the same. Hopefully that makes sense, or hopefully it's not confused you further. But yeah, basically the point is that we need to do, if you want to test for a conservative force, then we have the loop test, and the sign of a non-conservative force is basically this. Yeah. Okay. So then let's try this one. So the figure shows 3 paths connecting points A and B. Single force does the indicated work on the particle moving along each path. On the basis of this information, is the force conservative? Who thinks yes? Who thinks no? Yeah. Okay. Why do you say no?
For the bottom two paths, from A to B, it's 60, and from B to A, it's
Also 60. Yeah. So there's a loop here. So what's supposed to happen is that when you go in the loop, well, for a conservative force, that is, when you go in the loop, the total work is 0, right? That's actually true for another loop here. So for example, you go here, A to B along this path, that's minus 60. Say you go back along this path, that's minus 60 and 60. So it's 0. So in our kind of hiking example, you go from A to B and then, back, and then basically you gain that potential energy that you kind of lost. But here, what's going to happen is that you go from A to B, you gain 60. You go from B to A, back here, you gain 60 again. So you're up 120. Over here, now you're up 180, 210. So actually, you can just go in this loop and just keep on gaining energy. So, this would be great if it was like money or something. But so often, energetically, often money, it's also impossible to find such a loop. But also with energy, it's also kind of quite difficult to find a loop. In fact, it's probably impossible unless there is basically some source of energy behind that loop, which is going to drive the system to have more and more and more energy. Right? So if there's some other thing that's giving that energy, then that would be allowed. But generally, if this was just some natural thing, that would be a kind of a loophole in the universe where you could just keep on gaining energy. And generally, it doesn't really exist. Okay, so this is a non-conservative. It's not a conservative force. Okay. Right, so now we can get on to actually talking about quantifying what the potential energy is, and to some extent we basically already know what the formulas are, because it's basically the same formula as for work, except it's got a negative sign on it. So we knew from the last chapter that the general formula for work is this right-hand side without the minus sign. So you integrate the force from the initial position to the final position, and that's equal to the work. Now, here we just got a minus sign, so it's basically going to flip the sign of this, so mg times the difference in the heights, but then because of the extra minus sign, it's actually y final minus y initial. And often what you do is actually you can add a offset to this whole potential energy, and because this thing only includes a difference, it doesn't really matter that you add this this constant to it. So for example, if you can define this, for example, the gravitational potential energy, sort of the absolute value of this, for example, with reference to, say, sea level, right? So say the ocean is here, right? So we could define basically the gravitational potential energy to be mgh, where this h is defined with respect to sea level. And it wouldn't really matter that say somebody else used a different convention. Say somebody decided to use different convention, so it's not from sea level, but it's, I don't know, for some house halfway up the mountain, right? So we could define the potential energy in that way, and wouldn't really matter because say if you were comparing the potential energy between 2 points. So for example, according to the sea level convention, point A would have gravitational potential energy of 0, and this point B would be mgh. But for the convention with the house, for example, let's say this is sort of halfway up the mountain, right? So say this is h over 2. Convention with the house, basically you're starting sort of h over 2 down, right? So for this convention, it'll be a half mgh, because with reference to the house, you're halfway down the mountain. And then here would be a half mgh with a positive sign, and okay, maybe I should put a dash here. And regardless of which convention you use, the change in the potential energy, which is UA minus, well, maybe I should say, maybe I should say BA, so because this is sort of the final and the initial. So regardless of which convention I use, the difference is the same. It's still mgh, regardless of if I use sea level convention or the conventional convention with the house. And basically this is because, it's basically because all our formulas are always to do with the change in the potential energy. So if you notice, we have some formulas saying, change in kinetic energies work, and that's actually eventually equal to minus the potential energy. But basically all our formulas with the potential energy are got to do with changes in the potential energy, and the actual value of U itself is kind of doesn't really appear in any kind of physical quantities. So that's why we can have a kind of an arbitrary zero point of this gravitational potential energy. So yeah, so that's basically what this thing is saying. We can add a constant to it, doesn't really matter. Same for the elastic potential energy. We can actually set the 0 point of this to be anything we want, but usually it makes just a lot of sense to choose the 0 point of the elastic potential energy to be at the equilibrium position. So this is the relaxed position of the spring, and we can set the potential energy at that point to be equal to 0. So basically we can define the elastic potential energy to be this, and so when x is equal to 0, that's the x is defined as the position away from the relaxed position, then at x equals 0, u is equal to 0, but when you displace it by some x, it's has some potential energy. Okay, so let's try this one. So particles to move along an x-axis from x equals 0 to x1, while a conservative force directed along the x-axis acts on the particle. the figure shows three situations in which x component of the forces varies with x. Okay, so this is force times position graph. Force has the same maximum magnitude in all situations. Rank the situations according to the change in the associated potential energy during the particle's motion, most positive first. Okay. All right. So it's going from 0 to x, and the force is changing here. So in this case, the force so force is in the positive x direction, but it's kind of weakening with position. So it's a relatively strong force at the beginning, and then kind of weakens towards the end. This one, the force is always kind of maximum that way. And here, this one, the force is actually in the opposite direction, but then kind of again weakens as you get to the final position. So which one would have the largest potential energy change? Most positive first, the largest positive potential energy change. Second one, right. So certainly that would have the largest work, right? So the work, we can work out according to work is the integral effects from the initial to the final. In other words, say for the second one, basically area under the graph, right? So this is force times position. Yeah.
Why is, I thought potential energy has a negative sign?
That's right, yes. So this has the largest work done by the force. But, so as you pointed out, potential energy is actually negative of the work. So actually because of this minus sign, the largest one will be actually the one with the negative area under the graph, which is going to be the third one actually. Yeah. And so this one would be the largest, the least in fact, because the work that itself is the largest, most positive, but because of the minus sign, it will be kind of most negative. So in order, it will be 3, 1, and 2. Now, just to get a little bit more of a feel for what's going on. So basically, what's happening in this third one here, just to visualize it a bit. So we've got some particles, one-dimensional, starting from, well, why don't we line it up here? Starting from 0, and as I said, the force is actually in the opposite direction to the movement, right? It's moving from here to here, right? So the displacement is basically that way, but then the force is that way. And as you go from here to here, it's weakening, but it's always in this way, yeah? So, well, from the work kinetic energy theorem, we can see that, let's say that, this particle's moving this way, this is going to be losing kinetic energy, sorry. Because basically there's a force that's pulling itself back. It's going this way, but then the force is acting in the opposite direction. But if you imagine that maybe this is some kind of spring or something, you're going this way, you're losing kinetic energy, but the spring is actually going to be tightening. And so at some point, well, that potential energy could turn back into kinetic energy, right? So that's kind of more or less the situation that might be happening there. It's not actually, the spring force would be the opposite, actually. For the spring force, it would look actually like this, right? In this case, we've got a weird-looking force that actually kind of weakens as you go further. So it's kind of hard at the beginning, but then it kind of gets easier as you go forward. But it's always pulling you back. For this one, it would be like something's pushing you. Something's pushing you all the way. So okay, so you're going to be gaining kinetic energy because this work is positive, right? But then that must be at the expense of something that's pushing you, and that something is losing potential energy. So that's kind of more of a physical picture. Yeah, okay, so this is probably the good place to, well, I'll just briefly mention that, this is obviously one of the central results of the chapter, so we should probably not just rush through it, let's just get a taste of it now. So we've worked out work is equal to change in kinetic energy, but work is equal to the negative of the potential energy. So essentially, as I've been kind of saying, the gain of one is the loss of the other, right? And so this is the idea of the conservation of mechanical energy, so that if you actually look at the total energy as a whole, then that will be conserved, for a conservative kind of force. So you can rewrite this equation, delta K equals minus U. So delta K, we're saying that delta K equals to the work is equal to also minus mu. So let's just look at the change in kinetic energy and potential energy. So if you look at this is K final minus K initial. And this has got a minus sign, but this is U final minus U initial. And we can just do a little bit of rearranging so that let's put this UF on the left and then the initial ones on the right here. So basically you'll have KF plus UF, is equal to KI plus UI. So basically it says that the initial and the final total energies in terms of kinetic and potential energies are going to be the same. So we can define this thing as kind of the total mechanical energy. And so in the isolated system where only conservative forces cause energy changes, the kinetic energy, potential energy can change, but the sum does not change. And yeah, okay, so maybe we'll just leave it there for today. Any questions? Okay, then that's it for today, and I'll see you on Tuesday.